Welcome back to the deep dive. Today, we're going to be looking at why, well, everything spins.
Ah, the universal spin cycle.
Right. And we've got a great source here packed with all sorts of fascinating insights about this fundamental phenomenon. Like, did you know that
Go on.
if you're an anchor out right now,
Oh, are we talking about speed?
you're moving at a dizzying 1,280 kilometers per hour just by standing still?
You don't say. It's the power of Earth's rotation.
Yeah, it's incredible. We don't even feel it.
Right. It's a great example of how even when we feel stationary, we're constantly in motion.
Yeah, exactly.
And to understand this universal spin, we need to grasp the concept of conservation of momentum.
Oh, okay, so momentum.
It's a fundamental principle in physics.
Okay, so is it basically the oomph an object has when it's moving?
Yeah, you could say that.
So, like a speeding train has way more momentum than I do when I'm taking a leisurely stroll through the park.
Exactly. And the law of conservation of momentum states that in a closed system, like our universe, the total momentum remains constant. It can be transferred between objects through collisions, but it never just disappears.
So it's always there.
Always.
So if you think about, like, two billiard balls colliding,
Classic example.
one's at rest and the other one's in motion.
Right.
The momentum from the moving ball is transferred to the stationary one, right, when they hit.
Upon impact.
And that sets the stationary ball into motion.
Yes, but the total momentum within that system, it remains the same.
Oh, okay, I see.
And this principle helps us understand how the universe got its initial spin from the Big Bang.
A Big Bang. Now, our source says the Big Bang wasn't a perfectly uniform explosion, right?
Absolutely not. There were tiny variations in density, imperfections that set the stage for the swirling cosmos we see today.
So, like, imperfections in the Big Bang led to everything spinning.
In essence, yes. Those initial density variations created pockets of matter with different amounts of momentum. It's these subtle differences that seeded the large-scale structures and their rotations.
Wow. Okay, so from those tiny initial imperfections in the Big Bang, we get swirling galaxies, spinning stars, planets rotating on their axis.
It's all connected.
It's all connected. Amazing. So zooming in on our own solar system then,
Yes.
we see that most planets, including Earth, rotate in the same direction around the sun.
Yes. And this common direction likely stems from the initial rotation of the vast cloud of gas and dust that birthed our solar system.
So that initial cloud was already spinning.
It was. And this angular momentum was passed on to the planets as they formed.
Okay, that makes sense. But then we have Venus and Uranus. They're spinning in the opposite direction. What happened there?
That is interesting, isn't it?
Yeah, could they have formed outside our solar system?
That's unlikely given their composition and position. A more plausible explanation lies in dramatic events in their early history.
Oh.
Massive collisions with other celestial objects could have disrupted their original spin,
Oh.
flipping their rotational direction.
So cosmic collisions act like a giant spin switch. That's incredible.
Yeah.
Now, our source gets pretty dramatic when talking about what would happen if Earth suddenly stopped spinning.
Yes. It paints a rather chilling picture. We have to remember inertia.
Inertia.
Yes. The tendency of an object to resist changes in its state of motion.
Okay.
So think about when you're on a speeding train that suddenly brakes and you're thrown forward.
Oh, yeah.
Except in this case, it's the entire planet coming to a halt.
Oh, wow.
If Earth were to abruptly stop rotating, everything not firmly attached to the ground, including us, would continue moving eastward at incredible speeds.
Oh, that would be bad.
Imagine being flung at hundreds of kilometers per hour.
Yeah, that's not good. What else would happen? I mean, it can't just be that,
Oh,
right?
it wouldn't stop there. Our source details a cascade of catastrophic events.
Like what?
Massive tsunamis engulfing coastlines. The atmosphere continuing to rotate, generating unimaginable winds.
Hold on, I'm having trouble picturing that. How could the atmosphere keep spinning if the Earth stopped?
Well, think of it this way. Imagine a bowl of water spinning rapidly. If you suddenly stop the bowl, the water inside will continue swirling for a while.
Oh, because of its own inertia.
Exactly. The same principle applies to the atmosphere. It has its own momentum, and even if the Earth stopped, the atmosphere would take time to adjust, leading to, well, catastrophic winds.
So we'd have the Earth not moving, but with the atmosphere still swirling around it.
Yes, like a furious, invisible blender.
Oh, wow. That's hard to even imagine.
It's a truly terrifying scenario to contemplate, and that's not all. In the long term, the effects would be equally devastating.
Oh, no. What else?
One of the most significant consequences would be the loss of Earth's magnetic field.
Right, the magnetic field. That's what shields us from the sun's radiation.
Yeah, exactly.
But how does Earth's rotation play a role in generating that?
Well, within Earth's core lies a molten iron outer core that's constantly churning due to Earth's rotation and internal heat. This churning acts like a giant dynamo, generating electric currents that in turn create the magnetic field that envelops our planet.
So it's Earth's rotation that powers this protective shield.
Precisely. And without that shield, the constant bombardment of solar radiation would render the surface of our planet largely uninhabitable.
So no magnetic field, no life as we know it.
Essentially, yes. Life as we know it would be impossible.
Wow, so a spinning Earth, that's not just a cool fact. It's essential for life itself.
Indeed. It raises an interesting question, though. Could life exist on a planet that doesn't spin at all?
A non-rotating planet.
Hmm.
I wonder, our source suggests it might be possible.
Albeit under very specific conditions.
This is where it gets really interesting.
Yeah.
What would life on a non-rotating planet even look like?
Well, our source points out some major challenges.
Like,
A non-rotating planet would have extreme temperature differences between its day and night sides.
so one side's super hot and the other side's freezing.
Yes. One side would bake under the constant glare of the sun, while the other would be plunged into perpetual darkness and freezing cold.
Oh, that doesn't sound very hospitable.
It would certainly limit the types of life that could evolve, but the source does offer a glimmer of hope.
A glimmer of hope. Okay.
It suggests that life could potentially adapt to these extreme conditions in specific zones.
In specific zones?
Yeah.
Like where?
Perhaps in a narrow band around the Terminator where day meets night?
Oh, the Twilight Zone.
Yeah.
So life might find a way, even in the most unlikely of places.
It's certainly a possibility.
That's pretty cool, actually. Are there any real-world examples that hint at the possibility of life on these non-rotating planets?
Well, we haven't directly observed a non-rotating planet, but there are some intriguing candidates out there that offer a glimpse into the possibilities.
Oh, like what?
Astronomers have discovered a class of planets called tidally locked planets.
Tidally locked, huh?
Yeah.
I think I've heard of that. That's where a planet always shows the same face to its star, right?
Exactly. Just like our moon is tidally locked to Earth.
Okay.
These planets are tidally locked to their stars due to gravitational forces that synchronize their rotation with their orbital periods.
So one side's always day and the other side's always night.
Precisely. And while we haven't found definitive proof of life on these tidally locked planets yet, they do offer a tantalizing glimpse into the possibilities.
Yeah.
Imagine a planet with a permanent day side and a permanent night side, each with its own unique ecosystems.
Oh, wow.
Perhaps separated by a narrow twilight zone where conditions might be more temperate?
It's like something out of a science fiction novel.
Indeed. But who knows, maybe one day we'll find evidence that life has indeed found a way to thrive on these strange and wondrous worlds.
It's definitely a possibility. Okay, so we've covered the origins of spin, the consequences of a sudden stop, and even touched on the possibility of life on non-rotating planets. But what about the different types of spin?
Oh, different types. What do you mean?
Well, there's the spin of a planet on its axis, and then there's the spin of a planet around its star. Are those considered different types of spin?
You're absolutely right to point that out. We often use the word spin interchangeably, but in physics, there's a distinction between rotational motion and orbital motion.
Okay.
When a planet spins on its axis, that's rotational motion. When it revolves around its star, that's orbital motion. And both are governed by the same fundamental principle, conservation of angular momentum.
Oh, so it's all connected. But
Right.
how exactly does angular momentum differ from, like, the linear momentum we discussed earlier?
Ah, that's a great observation. Linear momentum is associated with an object moving in a straight line.
Okay.
While angular momentum is associated with an object rotating around an axis, think of a spinning figure skater.
Okay.
When they pull their arms in, their rotational speed increases.
Yeah, why is that?
Well, because they're decreasing their moment of inertia, essentially how spread out their mass is. And to conserve angular momentum, their rotational speed has to increase.
Ah, I see. So the more compact an object is, the faster it will spin for a given amount of angular momentum.
Exactly.
That makes sense. But what about the scale of spin? I mean, we've been talking about planets and stars, but does the concept of spin apply to even smaller objects like atoms?
Absolutely. In fact, spin is a fundamental property of subatomic particles like electrons and protons.
Wow.
These particles have intrinsic angular momentum, meaning they're always spinning even when they are at rest.
Hmm.
And this intrinsic spin plays a crucial role in determining their properties and interactions.
Wow. So spin isn't just a large-scale phenomenon. It's woven into the very fabric of matter itself.
It is.
That's incredible. And I'm guessing this spin at the subatomic level has consequences for the larger scale universe as well.
It most certainly does.
Like what?
The spin of subatomic particles influences the behavior of atoms, which in turn influences the behavior of molecules and so on, all the way up to the macroscopic world. For
Wow.
instance, the spin of electrons is responsible for magnetism, a force that plays a crucial role in everything from the formation of stars to the functioning of our brains.
So from the tiniest particles to the grandest cosmic structures, spin is everywhere.
It's a beautiful and intricate tapestry woven together by the laws of physics.
It really is.
And it's through understanding these fundamental principles that we can truly appreciate the complexity and wonder of the cosmos.
Well said. And with that, I think we've covered a lot of ground in this first part of our deep dive into the world of spin. We've explored its origins, its consequences, and even touched upon its role in the microscopic world.
And there's still much more to uncover.
Yep.
In the next part, we'll delve deeper into some specific examples of spin in action, from the swirling of galaxies to the intricate dances of binary star systems. We'll also explore some of the cutting-edge research that's shedding new light on this fundamental phenomenon.
Sounds good.
I'm looking forward to it.
Me too.
And welcome back to the deep dive. We've laid some fantastic groundwork, understanding not just the basics of spin, but also dipping our toes into the truly mind-boggling implications it has on life, the universe, and everything.
Yeah, it's amazing to think that something we experience every day, like the cycle of day and night, is a direct result of these complex physical laws governing spin.
It is. And as promised, let's take a look at some specific examples of spin in action across the vast canvas of the cosmos. Our source mentions this fascinating phenomenon of galaxies rotating in similar directions, at least within certain clusters.
Right, like a synchronized cosmic ballet.
Hmm.
But how do we even know that galaxies are spinning in similar directions? I mean, they're so far away.
Well, astronomers can study the light emitted by galaxies
Oh, okay.
and analyze its spectrum.
Spectrum.
This reveals the motion of stars and gas within the galaxy. For example, in a spiral galaxy, like our own Milky Way, one side will be moving towards us, causing a blue shift in its light, while the other side will be moving away, causing a red shift. By observing these shifts, we can determine the direction of rotation.
Ah, okay, so we're using light itself to unravel the secrets of galactic spin. And what have astronomers found? Are most galaxies spinning in the same direction?
Not quite. It's more nuanced than that. While there's a tendency for galaxies to align their spins within a cluster, it's not a universal rule.
Okay.
It's more like a cosmic dance with partners occasionally switching steps.
I like that analogy.
For instance, in the Coma Cluster, a massive gathering of over 1,000 galaxies, there's a slight preference for galaxies to rotate in a clockwise direction when viewed from Earth. But it's not a perfect alignment.
So there's preference, but there are exceptions. What could cause those exceptions?
One possibility is that these galaxies experienced gravitational interactions or even mergers with other galaxies in the past. Such events can disrupt their original spins, causing them to deviate from the overall pattern.
So it's like a cosmic billiards game, with galaxies bumping into each other and changing their spins over billions of years.
Exactly. It makes you realize that the universe isn't static. It's constantly evolving and interacting.
It really does. And speaking of interactions, our source also touches upon the captivating world of binary star systems.
Ah, yes, binary stars.
These systems, where two stars orbit around a common center of mass, provide a stunning showcase of spin and orbital mechanics.
They do indeed.
I love binary star systems. They're like a celestial waltz, with two stars locked in a gravitational embrace.
A beautiful analogy.
But I'm curious, how do their individual spins and orbital motions influence each other?
Well, imagine two spinning tops orbiting each other. Their individual spins and their orbital motion around each other are all intertwined.
Okay.
They can transfer angular momentum between each other, causing their spins and orbital periods to change over time.
So it's a delicate balancing act, with these stars constantly influencing each other's movements.
Precisely.
And what happens when these stars get too close?
That's where things can get really dramatic.
Oh.
If the stars are close enough, their gravitational interactions can become so strong that they start to distort each other's shapes, pulling out streams of gas and creating stunning visual
So
displays.
they're practically touching.
Almost, it's like a cosmic tango, with these stars getting closer and closer.
And I imagine these interactions can have significant consequences for their individual spins as well.
Absolutely. These close encounters can speed up or slow down the star's rotations, or even cause them to flip their spin axes entirely. It's a testament to the incredible power of gravity and the fascinating interplay between spin and orbital motion.
You know, it's amazing to think that we can actually observe these dramatic events unfolding millions of light years away. We're
Mhm.
witnessing the intricate dance of gravity and spin on a cosmic scale.
It is a privilege to witness these cosmic ballets. It's a constant reminder of the beauty and complexity of the universe.
It is.
And as our technology advances, we're able to study these systems in ever greater detail, unlocking more secrets about the role of spin in shaping the cosmos.
It's mind-blowing to think about the cutting-edge research happening right now that's revealing these secrets. But I'm curious, are there any particular breakthroughs or discoveries that have surprised you recently?
There have been many exciting advancements, but one that really stands out is the discovery of fast-spinning millisecond pulsars.
Millisecond pulsars. Those sound intense. Tell me more.
They are. Pulsars are incredibly dense, rapidly rotating neutron stars that emit beams of radiation from their magnetic poles.
Okay.
These beams sweep across space like a lighthouse beacon, and we detect them as pulses of radio waves.
I remember learning about pulsars in school, but what makes millisecond pulsars so special?
Well, as their name suggests, they rotate incredibly fast, completing hundreds of rotations per second.
Wow, that's fast.
These extreme rotation rates are thought to be the result of a process called accretion spin-up,
Accretion spin-up.
where the pulsar pulls in matter from a companion star.
So it's like a cosmic figure skater pulling in their arms, causing their spin to accelerate.
Exactly. And what are the implications of these incredibly fast spins?
Yeah, what does it mean?
They provide us with unique laboratories to test some of the most extreme predictions of Einstein's theory of general relativity.
Oh,
For instance, the intense gravity around these rapidly spinning pulsars can warp spacetime, creating a phenomenon known as frame dragging.
frame dragging. That sounds like something straight out of science fiction. What does that even mean?
It's a mind-bending concept, but essentially it means that the rotating pulsar drags spacetime along with it, causing nearby objects to be pulled along as well. It's a bit like stirring a cup of coffee and noticing how the swirling motion drags the coffee grounds along with it.
Wow, so these pulsars are not just spinning incredibly fast, they're actually twisting the fabric of space-time itself. That's incredible.
It is, and it's a testament to the interconnectedness of the universe, where even the smallest particles can have a profound impact on the largest scales. And as we continue to explore the cosmos, I'm sure we'll uncover even more surprising and awe-inspiring examples of spin in action.
I can't wait to see what we discover next.
Ah,
Okay, so we've journeyed from the synchronized spin of galaxies to the whirling dance of binary stars, and even dived into the mind-boggling world of millisecond pulsars. But before we wrap up this part of our deep dive, I have one more question that's been nagging at me.
oh, go on, I'm all ears.
We've talked about the possibility of life on non-rotating planets, but what about the opposite extreme? Are there any known planets that spin at incredibly fast speeds, and what would the conditions be like on such a world?
That's an excellent question. And yes, there are planets out there that spin much faster than Earth. One example is the exoplanet Beta Pictoris b,
Beta Pictoris b, okay.
a gas giant that's estimated to be spinning at a staggering 100,000 kilometers per hour at its equator.
Whoa, that's fast.
It's almost 25 times faster than Earth's rotational speed.
Wow. What would it be like to stand on a planet spinning that fast?
Well, for starters, you'd experience incredibly strong winds
Okay.
and possibly even supersonic storms.
Oh, wow.
The centrifugal force would also be much greater, meaning you'd weigh less at the equator than at the poles. And the days and nights would be incredibly short, possibly lasting only a few hours each.
It sounds like a wild ride. Would such a planet even be habitable?
Habitability on such a world would face significant challenges.
I can imagine.
The extreme weather patterns and short day-night cycles would make it difficult for life as we know it to evolve. But who knows? Perhaps there are life forms out there that have adapted to such extreme conditions.
It's a fascinating thought. And it just goes to show that the universe is full of surprises. There's still so much we don't know about the diversity of planets out there and the potential for life to exist in ways we can't even imagine.
Absolutely. Every new discovery pushes the boundaries of our understanding and reminds us that we've only just begun to scratch the surface of what's out there.
Well said. And with that tantalizing thought, I think it's time to spin our way into the final part of our deep dive. We'll be right back after a short break to wrap things up with some concluding thoughts and maybe even a few predictions for the future of spin research. And we're back for one final spin as we wrap up our exploration of why, well, everything in the universe seems to be spinning. It's been a pretty wild ride so far.
It has been quite a journey. We've gone from those massive swirling galaxies to the tiny little dances of subatomic particles. And it's amazing that it's all connected by this, this fundamental principle of spin.
Yeah, like a hidden code that unlocks the secrets of the cosmos, right? But it's not just about movement, is it? It's a force that shapes the very structure of the universe. I mean, it influences the formation of stars, galaxies, even life itself.
You got it. It's a reminder that even the things that seem really simple can have some pretty profound implications when you really look deeper. And our source here, it doesn't just tell us how things spin, but also hints at the why.
Right. It all goes back to those tiny little imperfections in the Big Bang, right? Those initial variations in density. They were ultimately the seeds that led to this swirling, cosmos that we see today.
You got it. And it's not just the Big Bang. We have to think about the nature of gravity itself. It plays a pretty crucial role, too. You see, as matter clumps together under the influence of gravity, it naturally starts to spin.
So gravity isn't just pulling things together, it's making them spin. Like the universe has this built-in tendency towards rotation.
Exactly. And this tendency, it's not limited to, big celestial objects. Remember, even those tiny subatomic particles, they have that intrinsic spin, that inherent angular momentum. It's a part of their very nature.
It's amazing to think about that spin at the subatomic level can have such a big impact on the universe as a whole. It's like a chain reaction, from the tiniest particles to the largest structures, all connected by this invisible force.
It really highlights how interconnected everything is in the cosmos. And as we've seen, the study of spin has led to some pretty exciting discoveries in astrophysics. Think about the detection of gravitational waves or mapping the cosmic microwave background radiation.
Absolute mind-blowing, some of the advancements that have been made just in the past few decades, really. But I'm curious, where do you think spin research is headed in the future? What are some of the big questions that scientists are trying to answer?
Well, one area that's got everyone buzzing is the search for primordial gravitational waves.
Oh, yeah, primordial gravitational waves. I've heard about those. They're like echoes of the Big Bang, right?
Right.
But how does spin tie into this search?
Well, these primordial gravitational waves, they would have left a unique imprint on the polarization of the cosmic microwave background radiation, that afterglow of the Big Bang. And by studying the patterns of this polarization, scientists are hoping to detect the signature of these ancient waves.
So it's like we're searching for a whisper from the dawn of time. A faint little echo of the universe's first moments.
That's a great way to put it.
And spin is a crucial part of this search.
Oh, it is. The polarization patterns that scientists are looking for, they're directly related to the spin of the particles that interacted with these primordial gravitational waves.
So it's like a cosmic detective story, right? Using those clues left behind by spin to unravel the mysteries of the early universe.
Exactly.
It's incredible to think that we can actually look at these events from so long ago using, the tools of modern science. It makes you realize that the universe isn't just this vast expanse of space and time. It's a story, a narrative that we're slowly piecing together.
I love that. Beautifully put. And as we keep digging deeper into the mysteries of spin, I have no doubt that we're going to uncover even more chapters in this grand cosmic story.
I can't wait to see what we learn next. Well, folks, it looks like we've come to the end of our whirlwind tour of the spinning universe. We've explored its origins, talked about what happens if it all suddenly stops, and even gotten a peek at how it works at the smallest level.
And hopefully we've left you with a sense of awe and wonder at the intricate workings of the cosmos.
Oh, absolutely, because as we've learned today, spin, it's not just some random quirk of nature. It's a fundamental force that shapes the universe as we know it. It's a reminder that even in the vastness of space, even the simplest principles can have huge consequences.
Couldn't have said it better myself. And with that, we encourage you to keep exploring, keep asking those questions, and never stop marveling at the wonders of the spinning cosmos.
Well said. Until next time, keep those minds spinning, and thanks for joining us on the Deep Dive.